All right, so this is going to be our second example. Over, if you'd like to just add on to your notes that you wrote on the first one, rather than having two separate sheets, it'll be easier to upload online and for me to give you credit for it. Great. So just add on to the other one. You can put example 2 if you want. If you want to write the question down, you can do that. It doesn't really matter. But we're going to go through this final example. There are only 2 different types of problems you're going to see with this section, with the chi-square goodness of fit. That is what we just did, where they put the actual percentages, saying, hey, it's supposed to match this distribution. And the other one is when you're trying to test to see if it's uniformly distributed. So I'm going to go and read the problem, and you'll see where that's popping up and how you can tell. Another way you can tell is because nowhere in this problem are they listing the percents of each of these colors. There's a table, they didn't list them out, like 10% brown, 20% yellow. That's another dead giveaway to uniform. So I'll go and read the question. It says, a researcher claims that the number of different colored candies in bags of dark chocolate M&Ms is uniformly distributed. Bingo, right there. That's telling me that this is the other type of goodness of fit problem that we have to deal with. Okay. So that's big. All right, so now we know it's uniformly distributed. We'll talk about what that means in a sec, but let's finish reading. To test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. The results are shown in the table on the right at a significance level of 0.1. That's the researcher's claim. Okay, so uniformly distributed means that they are all the same percentage. So you're saying the same percent of brown is yellow, is red, is blue, is orange, is green. Every single color in the M&Ms consists of the same percentage. Okay, so nowhere does it say what that same percentage is, but we can easily figure that out with a quick little calculation there. Okay, so uniformly distributed is the key word here. I'll underline it again. That is showing me that I'm going to do what I'm going to do for this problem. Now, once again, there is no parameter for this. You don't have to define brown, yellow, red, blue, orange, green. You just have to write HO and HA in words. So the way we write that's going to be a little different. I'm going to go ahead and type it again. I had good luck with that last time. Make it a little bit smaller. So HO is going to be that the distribution of colors of M&Ms, and our assumption at the beginning is uniformly distributed. Okay, so HO will always be the distribution of whatever the problem is about is uniformly distributed. Let's go ahead and fix that. All right. Is uniformly distributed. So you could probably take a really good guess about what HA is. What HA is then. So HA, probably should just leave it at 36. Okay, HA. Oh boy, that's lots of good stuff going on there. Okay, hold on. All right, there we go. Okay. So HA is going to be the distribution of colors of M and M's is not. All right, having capital letters obviously don't do that, but that's the key difference, is not uniformly distributed. All right, that's it. So anytime you're talking about uniformly distributed, like I've underlined, HO as always they are, assume that they're the same percentage of each color. HA, and let's try and prove that it's different than that. All right, so there's HO, HA. Next step we have to do is find our chi-square value. So remember from the last video, we'll recap. Chi-square is equal to the observed minus the expected squared divided by the expected. So recall from the last video that these are our observed values. And we have to find the expected ourselves by multiplying the total by the percent. Now, in this problem, they once again gave me the total. I don't think that's always going to happen. Do not assume that is going to be the case. If I didn't have that, all I'd have to do is add all of these together. And if you add all those up, you're supposed to get 500. So let's say that wasn't here. Then you'd have to just add the 80 plus the 95 plus the 88, 83, 76, 78, and it will give you the total. It may not be a nice number. It may not be a pretty number like 500, and I think the last problem was pretty too, 300. But just add those up. That's n, the total. So now that we have that, I should probably keep that. So that was important. This is important. We need to figure out the percentages. So this problem does not give me the percentages. You have to find them yourself. So if they're uniformly distributed, that means each of these has to be the same percent. It's very easy to figure out what that same percentage will be. You count how many categories you have. 1, 2, 3, 4, 5, 6. And each of those are going to make up one part of the 6. So one part out of 6, another way to say that is 1/6. So all of these are going to be whatever 1/6 is. Now, if we put that in there, we're going to get a repeating decimal. And anytime you have a repeating decimal, if you write that decimal, you're going to have rounding error. If you put 0.167, which is what that is, you're going to have a continuous rounding error for every single part of the problem. So we cannot do anything but leave it as 1/6 when it is a non-terminating decimal. Okay, so anytime it's uniformly distributed, you just take 1 divided by the number of categories. That's it. If it was 5, and for some reason we had 5 categories, took out green, it'd be 1/5. Now 1/5 is 0.2. You could use 0.2 because it's a terminating decimal. We have 1/6 that doesn't terminate. We're going to have to use 1/6 the whole time. So, however, if all of these are 1/6, then I only need to do this once. Because if I'm expecting the same percentage from each of these, then the expected for each of these is going to be the same number. So uniformly distributed is actually a little bit nicer once you understand how to get that percentage, because then I only need to do the calculation once. So to figure that out, let's go to our calculator. We're going to do 500 times, and I'm going to put in parentheses just to be safe, but you probably don't have to. So 500 times 1/6, which gives me 83.333. Now I'm okay with rounding there. We'll live with it. It's possible that when you do the quizzes that I did not round at all, so your answer might be slightly off, but it's not going to be far enough away where you wouldn't be able to figure it out. So I'll use 83.333 for this. All right, so then to find chi-squared, all the expecteds are 83.333. So I'm going to take my first observed, which is 80. So I'm going to do 80 minus 83.333 squared divided by 83.333. Now I have to do this for all of them. I'm not going to write every single one out this time. You should be able to see the pattern that's going on. And we are going to type all of them in the calculator anyways, so I'm not going to bother writing it out. Instead, and you can do this for any work that you do, your workbook problems you'll have to do, just put a plus dot 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 plus. And then my last expected is a 78. So then we'll do 78 minus 83.333 squared divided by 83.333. And that's all the work I have to show. So now I need to type this all in our Google calculator. We'll leave it right here for you. So obviously I'm supposed to write all the expecteds. I should have a total of 6 fractions here, but the plus dot 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 plus is sufficient for work. So I'm going to go back up here. I'm going to move this to the side because I need to see that table still. Let me move this over. And I will type all these in. So I am pulling this from these numbers here. Right? And all of them are 83.333, so that makes it really easy. All right, so We have 80 minus 83.333 squared divided by 83.333. I wish there was an easier way to do this, but there really isn't. Unless you can find a calculator, do it, feel free to, but this is what we're at. So 95 minus 83.333 squared divided by 83.333 plus, let me keep going, we're at 88, that's the yellow, minus 83.333 squared divided by 83.333 plus, we're on blue, which is 83. So 83 minus 83.333 squared divided by 83.333. If you get the pattern here, just skip ahead like a minute and you'll see what the answer is. If you just love hearing my awesome voice, feel free to keep listening. 83, whoops. 0.333. Hit the C button if you mess up. Luckily, it doesn't clear the whole thing, just the last number, so that's good. And I forgot my squared. So squared divided by 83.333. That was orange, so now I am on green. So plus parentheses 78 minus 83.333 squared divided by 83.333. Now, if I did this right, this should be a small number. You'll notice that a lot of the observes are very close to 83.333, with the yellow being a little bit far away. So I don't think this is going to be big. Let's go ahead and take a look. 3.016. There you go. So that is our chi-square value, and all of the tedious math is done. So you're going to need to make sure you're really careful typing that in. However you choose to type in, I would not use your phone. The phone is going to mess up order of operations beyond all doubt. So just 3.016. The Google calculator works great. Okay, it's a pretty good calculator considering what it actually is, just on Google. So chi-square is equal to 3.016. All right, ready for our p-value? We're almost done, guys. So this is the home stretch. So remember from the last video, degrees of freedom is a number of categories minus 1. So we had 1, 2, 3, 4, 5, 6 categories. So degrees of freedom is going to be 5. And remember, it's always an upper tailed test. It will always be a greater than right there. You never have to think about it. So now we're going to go to our p-value calculator. Make this big. So click on here. We have 3.016 and degrees of freedom was 5. Calculate, it should be a pretty big p-value, and it is 0.69752. So 0.698 will be fine. 0.698. Okay. So 0.698. And it doesn't really matter what alpha is. It's huge. It's a huge p-value. We're going to fail to reject. So recall that whenever your p-value is greater than alpha, you fail to reject HO. So we're ready for our conclusion. So since my p-value is greater than alpha, I fail to reject HO, which means there is no evidence HA is true. So remember, your conclusion is always written in terms of HA. All right, HA. Do not look at HO. We're done with HO. It's always written about HA. So just rewrite that sentence. Say there is no evidence. Rewrite the sentence. You're done. So there is no evidence. I'm sorry, the next spot. There is no evidence that the distribution of colors of M and M's is, once again, not, because HA is not. So not, but not, you're wrong, is not uniformly distributed. There it is. So that's how you deal with uniformly distributed. It's very similar. I'm going to argue it might be a little bit easier because, remember, Those expected values are always going to be the same number over and over and over. See, they're down there too. Just remember that to find that percentage. So when you do the total times the percent, make sure total times percent, and that does not look like total. Make sure the percentage is always the number or 1 divided by number of categories, and you'll always be right. That's those categories. All right, so hopefully that was a helpful video. Now that you've seen the only 2 examples that will pop up anywhere with goodness of fit. Remember, this is a chi-square goodness of fit test still. It's just a uniform instead of a matching. And you're ready to go. So if you do have any questions, once again, you can reach out to me in a multitude of ways. I will happily walk you through how to do this if you're not getting things to match up. So hopefully this is helpful to you now that you've seen both types. You're ready to submit your notes. If you want to submit them right now after you finish writing all this out, you can do that for your grade and move into the bookwork whenever you are ready, or jump right into the quizzes if you'd like to do that. And thanks for watching.